Let's take a look now at section 15.6 and talk about surface integrals. Throughout this course, we've seen integrals over a region, where we take a region in the xy plane and take an integral by adding all of the points that are associated to that region. So you might have something like, here's a region R. To every point in R, we assign a value, right? F of x comma y. And if we add up all the f of x comma y's throughout, we end up with a double integral over area. Something like this. Right? We've taken something where we have a solid region in 3 space. And to every point in that region, we assign, again, an f of, and instead of x and y, because it's no longer on just a plane, we have a function of f and y and z. And if you were to take up all of the f of x, y, z's that are given by mapping these points by this function, you would get a triple integral over volume. Okay. And of course, in the last section, we saw how we can handle surface area by taking a solid, not a solid region, but simply a surface, the outer skin of some object, and saying, okay, if at every point here I assign a value, an f of x, y, z like this, and if I add those all together, that's going to be an integral over surface area. Here we said, oh, even though this is in 3 space, we can parameterize this as functions of 2 dimensions. So here we can write this as f of uv, right? We can parameterize it using 2 variables, so we can get away with using a double integral rather than a triple integral. Right? But then we've seen in these sections, when we define the double integral and the triple integral, that while this gives us an area, we can always take a double integral of a function over that area. And while this gives us a volume, we can always take a triple integral of a function with respect to volume. This wasn't always like this. You could have triple integral of f of x, y, z dv. Same thing here. Even though this gives us a surface area, we can now integrate a function with respect to this surface area. That's called a surface integral. Right? So that's what we're talking about in this section. We're talking about surface integrals. And just like these, you say every point on this curve, we're mapping a function to every point on here. And if we then add all those together, that's going to be a double integral over the surface area. So here, just like this yields a double integral over f of x comma y dA using a function that maps every point in here, to a value, in this case a z value. Just like this can yield a triple integral of a function with respect to 3 variables. Likewise, this will yield a surface integral when we take an integral with respect to the surface area of a region, of a function rather. I guess it'll be R. Right? Okay, so now how do we do that? Well, we have a theorem here that tells us how to do that. And incidentally, the proof of this is basically trivial. It takes what we worked very hard for in the previous section and essentially just adds one more thing to it. So here we say let S be a surface given by Z equals G of X comma Y. Here we're going to take all of our surfaces to be, you have a region in the XY plane. You have a region R in the XY plane. And you can take this region R and take every point in that region and apply a function to it, and that'll give you a height. And that height over that region, R, gives you your surface S. So S is a surface given as a function of a region in the plane, in the XY plane. Technically, this could also be in the XZ plane or in the YZ plane, but for the most part, our illustrations will always be in terms of the XY plane. It can work in any plane. You just have to change the variables that you're dealing with. Okay, so let S be a surface given by Z is equal to G of X comma Y, and let R be the projection of S onto the XY plane. In other words, this one right here. Take this and squash it down here. It's basically just the domain of that function that gave you Z. Okay, so now let G, some function G, which gives you your surface, and the partial derivatives with respect to X and Y. After all, that is a function of X and Y. You can take the partial derivatives with respect to either. Let the function and its two derivatives be continuous on this region R, on the XY plane, X and Y. And let F be an, oh, and I guess I should write F of X, Y, Z, but it's okay. I'll write that over here as well. F of X, Y, Z should be continuous on the surface S. So G lives down here and F lives up on the surface. Assuming that those things are true, the double integral of F of X, Y, Z with respect to surface area is given by the double integral over R of F of X, Y. Here, we're going to do this as a double integral, so we can't have three variables, but that's okay because here we know Z is equal to a function of X and Y. So we don't leave it as function of X, Y, Z. We write it as function of X, Y, and another function of X, Y. All right, we can't use a third variable because this is a double integral. Okay, so that's F of X, Y, G of X, Y, times the square root of 1 plus the partial of X squared plus the partial of Y squared under a square root with respect to A. Here, I guess I'll call this a proof, although it is essentially just taking what we did last time and just adding an extra factor. So recall that we saw from a previous section that the delta S sub I, a little tiny bit of surface area, is given approximately by the square root of 1 plus G sub X squared plus G sub Y squared. Right? This is when we first define surface area and when we first define an integral to give us surface area. We make this approximation, all right? And that is, with respect to A. Right? So here our little change in S is approximated by a little change in A times that result. So if you wanted to take the sum as I goes from 1 to n of F of X comma Y comma Z delta S sub I, that would be approximately the same as the sum as I goes from 1 to n of F of X comma Y comma Z. And I guess I should say xi, yi, and zi, since there are different ones. Okay. Times, well, this is approximately the same as this one. So this would be f of xi, yi, zi times 1 plus g sub x squared plus g sub y squared delta a sub I. But now you're done. Because now if I take the limit of both sides, by taking the limit as n approaches infinity, as the norm of our partitions all approach 0 of both sides, we get that the sum as I goes, I guess that limit simply becomes an integral over a surface area. As we've seen before, an integral over a surface area is written this way: the integral over the surface S of f of x comma y comma z ds, and that's going to equal to, this becomes an integral. Notice you're integrating with respect to area, so that's going to be an integral over a region R with respect to area of f of x I comma y I comma z I square root of 1 plus g sub x squared plus g sub y squared. But of course here, that is a function of 3 variables. And we're supposed to be taking a double integral, which means that one of these variables will not be accounted for. Oh, sure, but after all, z is a function of x and y. Okay, so here we can write this as the double integral over r of f of x. Oh, I guess I don't need sub I anymore. I've already taken the limit. So this would be f of x comma y square root of 1 plus g sub x squared plus g sub y squared dA. Here, this y, this x and y, or this x and y, this z is also a function of x and y. If you want to be a little more explicit about it, you can even write it as the double integral over r of f of x comma y comma g of x comma y. Here, you could be explicit about it. After all, z is that specific function of x and y. Times the square root of 1 plus g sub x squared plus g sub y squared dA. And that's it. So basically, last time we worked very, very hard to prove that this approximates that. And now we just said, oh, and by the way, if we just throw that extra thing in there, well, it doesn't really bother us. So just go ahead and throw it in. So the proof of that one is essentially trivial. For the most part, this section will be based on examples. We're going to go ahead and take a look at lots of examples of how surface integrals work. And we'll wrap up with a particular kind of surface integral, which is of interest to us, called the flux integral. But first, let's just take a look at some regular surface integrals. So as our first example, we're going to go ahead and evaluate the following integral. Evaluate. We're going to take the double integral over a surface S, x minus 2y plus z ds. Right? Note, over a surface, we're taking a surface area. And we're going to be given the surface. We're told that S is given by Z equals to 2/3 x to the 3/2. And we're given some boundaries on this. We're told, oh, and by the way, x is bound between 0 and 1, and y is bound between 0 and x. So x is bound between 0 and 1. And y is bound between 0 and x. Okay. All right, so let's take a look at that. First of all, this is not really required. We don't really require a drawing here, but I'm going to go ahead and make one anyway, just for a visual. Here, let me draw this in the xz plane. Okay, so here's x and here's z. And the x to the 3/2, that's going to be, well, something like this, more or less. You could always plot a few points, but notice this x value can't be negative. If you take a negative here, take the 3/2 power of a negative, you're going to get an imaginary number. So here this must be strictly positive. All right. And since that's got to be positive, well, then that's got to be positive. So it's going to be somewhere up here. You might say, well, there is no y variable. What's this about? Well, remember, whenever you have an object that has only two variables and one is missing, that means we're dealing with a cylinder. So if we take this onto 3 dimensions, our generating curve is this line here. If this is x, y, and z, then this curve here is essentially this curve here. And now we have rulings that are parallel to the missing variable, or in other words, they're parallel to the y-axis. So it would be something like this. It's kind of like a bent sheet of paper or something like that. Basically, you have a sheet of paper that comes back and touches the y-axis, and then once it touches the y-axis, it sort of just bends up toward you. Right? Here it's touching the y-axis, and then as it moves away from the y-axis, it's bending upwards away from there. So now here, this makes a little more sense. Now this tells us, well, look, if this goes on forever, that integral can't be convergent. This is going to keep on going and going and going. Oh, okay, but we're going to limit it. We're going to limit this on the xy plane. Here, x is between 0 and 1, and y is between 0 and x. Okay, so if y equals 0, that's that line. Y equals x, that's that line. So I got to go from my lowest here to my highest here. And then from left to right, I'm going to go as far as 0 here and as far as 1 here. So even though this does go on forever, I don't want all of it. I only want this section down here, the part that's over this triangle. Right here. So let's maybe make that drawing so that it actually is parallel. There we go. So here's my region on the xy plane, and what I really want is a surface that's over here. So here you could follow this up, and you could trace out that piece of my surface up there. which I'm not even going to try, but whatever. It's up there somewhere. So if you follow this up, it's the part that's directly over this triangle. Okay, so let's go ahead and set that up. For most of these problems, the setup will be the complicated part. Once it's set up, it's just a double integral. You can use Fubini's theorem. For the most part, setting up is the part that's going to be complicated. Once it's set up, it's usually not very difficult to complete. Usually. Sometimes integration can be rough. Okay, so by our theorem, that's going to be equal to the double integral over R of, and again, R is this surface down here on the xy plane. It's this one over here. And that's your R. It's the double integral over R of f of x comma y comma g of x comma y. We don't want to leave 3 variables. We can only use 2 since we're using a double integral. And then that's going to be times the square root of 1 plus g sub x squared plus g sub y squared over a. All right, so let's find out what all those things are. All right, so here we note from our theorem that g is just whatever function gives you z. So here g of x comma y is equal to just this thing right here. You'll notice it doesn't actually have a y in it, and that's okay. Sometimes it'll just be dependent on one variable, in particular anytime you have a cylinder. So here g of x is just that equation that gives us our surface. It only happens to have one variable, and that's okay sometimes. We are going to need g sub x. Okay, well, with respect to x, that's just a normal derivative. Take your 3/2 down, subtract 1 from the power, and that's x to the 1/2, like that. But don't forget, you're going to need to square that, so it's going to be g sub x squared, and if you square the square root of x, that's just x. And we're going to need g sub y, and the derivative of this with respect to y, well, with respect to y, that's just a constant. So here the derivative will be 0. And so 0 squared is still 0. Okay, so we're going to go ahead and write this as a double integral. Okay, so here this is our setup, right? This is the stuff that we need to plug in. So this is a double integral over R, we'll get to the boundaries later, of f of x, y, and g. So notice over here, we don't leave this the way it is. X's and y's stay exactly as they are, so x minus 2y stays as it is. But now z should not be z, it should be a function of x and y. All right? Oh yeah, but you know what that is, it's right here. That g of xy is that g of xy, it's the one that's defining your surface. So here we're going to write this as x minus 2y plus z. Oh yeah, but z is equal to that stuff right there. Z is equal to this function here. So this will be plus 2/3 x to the 3/2 power. And now that is being multiplied by the square root of 1 plus g sub x squared is just x. And g sub y squared, that's just 0. dA. All right, so now let's go ahead and put in our boundaries. Here, if you don't want to write the plus 0, obviously it's unnecessary. All right, so now we're doing a double integral over R. Now remember, R is this region here, this region on the xy plane. So here we're describing that region using our x and our y variables. Okay, so here I'll do it the way I usually do it, dy dx. You can do it the other way around if you like. So dy dx. Here I can describe my y variable, and really it's already described for me, right? Y is going from a low of 0 to a high of x, from 0 to x. My x value is going from 0 on the left to 1 on the right. 0 on the left to 1 on the right. So if this had been drawn for us, we would actually have to go through and try to map those as equations. But here, they tell us what the boundaries are. So that one's actually pretty nice. And then that's going to be x minus 2y plus 2/3 x to the 3/2 times a square root of 1 plus x. Okay. That first integral is actually pretty simple. Notice with respect to y, that's a constant. So we're not even going to touch that one. So now we're just going to take the integrals of these, right? So that's going to be the integral from 0 to 1 of, with respect to y, that one's going to be xy minus y squared plus 2/3 x to the 3/2 y. Everything's getting multiplied by y there. That one and that one. And then that's a constant. And when you take the antiderivative of a constant times a function, linearity tells you take the antiderivative of the function and then just toss the constant back in. All right, it's like if I'm taking the antiderivative of 5x, really I take the antiderivative of the x and then multiply by 5 at the end. Same thing here, that's a constant. Now that's being evaluated from where y is equal to 0 to where y is equal to x. We get that. And then here we're going to take the integral from 0 to 1. Let's go ahead and actually just plug these numbers in. So all of my y's are going to be replaced by x's. Okay, so that's that's x times x, so that'll be x squared, minus, that's also x squared, plus 2/3 x to the 3 halves times another x is x to the 5 halves, times the square root of 1 plus x, minus, and if I plug in 0 for all of those, I'm going to get 0, 0, and 0. Okay, so here some stuff simplifies. I have x squared minus x squared goes away, and I'm left with an integral from 0 to 1 of 2/3 times x to the 5 halves times the square root of 1 plus x. Like that. Just like that. Oh, and I guess I should say dx, right? Okay. Which is, you can factor out that 2/3 if you like. You can write this as the integral from 0 to 1, 2/3 times the integral of 0 to 1 of x to the 5 halves times the square root of x plus 1 dx. All right. That one looks nice and simple. It's not. I tried it ahead of time. It was, at first I tried a trig substitution. That actually would have worked, and it would have required a power reduction formula to be used 7 times consecutively. That wasn't very nice. I tried a hyperbolic substitution because I noticed I have the sum of squares, right? That's the square root of x squared, and that's 1 squared under a square root. That was slightly easier. It only led to 6 substitutions. I tried U substitutions. I tried a few of them. I sat here for about 30 minutes trying different substitutions. The shortest one that I was able to find was really rather long. So here I'm going to go ahead and stop, and I'm going to go ahead and say, and by the way, don't try to finish this one. I mean, you might. Like I said, it's perfectly doable. Your substitution would be something like this. You could say u is equal to x to the 1/2 power, and from that substitution, everything else eventually works out. It's just a very long, drawn-out problem. So here I would say, okay, and then of course you would get an answer, right? So here I'm going to say, I'm going to stop because this last integral is very long. It's doable. It really is. You can take x to the 1/2, use that as a u substitution. You'll change your variables, change your boundaries, and then you'll follow that up with a trig substitution or a hyperbolic substitution if you prefer that. And either way, it's rather long. So for the most part, this problem, you're concerned with how do you set this up. In the end, okay, yeah, that's a really long, really fancy looking integral. We're not too worried about that one. This is the part that matters. All right? You're going to take these. X's and Y's stay as they are. Z is being written using the surface. ds is the square root of 1 plus g sub x squared plus g sub y squared, where again g is our surface. And that's being integrated over the region in the plane, right? The boundaries on the xy plane over here. All right. So let's go ahead and take a look at another example of a surface integral. I've worked a couple of them ahead of time, and this one is significantly nicer in the end, the answer, but the setup is going to look very much the same. Okay, so let's go ahead and take the next one. Let's try the surface integral. So same kind of question. We're going to evaluate. And we're going to evaluate the surface integral over S of the square root of x squared plus y squared plus z squared. Notice the way that's written, x squared plus y squared plus z squared. That suggests that, oh, I have the sum of squares under a square root. Probably polar or spherical coordinates are going to be useful here. not guaranteed and not required, but anytime you see that kind of thing where you see sums of squares under a square root, you probably want to change your coordinates into cylindrical, polar, or spherical. But let's see. So here that's going to be the double integral over s of the square root of x squared plus y squared plus z squared ds, where s is going to be given to us by the equation z is equal to the square root of x squared plus y squared. And we're given some boundaries. In the last one, we were told the boundaries were, x is between here and here, and y is between here and here. In this one, we're given the boundaries in a slightly different way. We're given them as an inequality, as the solutions to an inequality like this. We're told x minus 1 squared plus y squared is less than or equal to 1. Just like over here, that's an inequality, but instead of separating them and saying, okay, here's what x is bounded by, and here's what y is bounded by, here they gave them to us as a single inequality. It's the same kind of idea, though. We're going to use that to give us our boundaries. So before we begin, it's useful to graph things out, or at least sketch things out. Here, if I have z is equal to the square root of x squared plus y squared, notice that what I have in my traces are, if x is equal to 0, well, that's going to be square root of y squared. Or in other words, it's the absolute value of y. If I take the xz trace, well, then I get z is equal to the absolute value of x. And if I take level curves of z, if I set z equal to constants, well, then I square both sides, and I end up with x squared plus y squared equals to a number. So those are going to be circles. So here I have linear sections on the xy trace and on the xz trace and on the yz trace. And if I look at level curves parallel to the xy plane, I get circles. Here, this is going to be a cone, right? That's a line, and these are circles. Okay, so they're lines if I look this way, but circles if I look this way. Like that. It's a cone. All right, but now remember, cones go on forever. They go on this way forever. In fact, they go on this way forever too. There is a part of the cone going down this way. So of course, we don't want the whole thing. We don't want it to go on forever. That's what this is about. This is giving us some boundaries. Here, this is a circle. Notice that's x squared plus y squared is equal to 1. So that's a circle of radius 1. But notice that I have minus 1 here. Okay, so whenever you take a graph and subtract 1 from the x variable, that moves everything to the right by 1. So here, this is a circle of radius 1, but instead of being centered at the origin, it's centered at 1, 0. Okay, so that's a 0, that's a 2, that's a 1, and that's a minus 1 down there. All right, so what that means is, yeah, I want that cone, but I don't want all of the cone. I only want the cone, the part of the cone that is on top of the circle of radius 1 that is centered at 1, 0. So that's my x, and that's my y, and that's my z. Here I have a circle of radius 1 centered there, and I don't want the cone, the whole cone. I just want the part of the cone that is directly over this region here. So that's something up there. Okay. And again, I'm not going to try to accurately draw that because, well, 3D is hard. So here, this is our R, this part in here, the circle on the plane, and it's probably a lot easier to see it if we look at that one, because after all, these are the same. Okay. So now, given that information, we have what we need to get this started. Go ahead and give that a try. See if you can set up the integral. You're going to write this instead of a double integral over s. You're going to write it as a double integral over r. Once you've written it that way, you're going to write it in terms of x, y, and z. That's probably not the best, because notice here, everything is in terms of a circle. Here I have the stuff over a circle. That's really screaming that I want to be using polar coordinates. All right, so give that a try. See if you can write this in terms of r over a double integral over r with respect to its area. And my suggestion is you write that in terms of cylindrical coordinates, polar and then the third variable stays z. All right? You can try to find the integral if you like or not. Here, the important part is the setup. Once you finish setting it up, go ahead and unpause the video, and we'll go through it together. All right, so let's go ahead and do this one. We're going to take this to be the double integral over r, where again, that's r, this region here, that circle on the xy plane, or I guess I should say the disk, because it's all the stuff inside, of the square root, and I'm going to start this off in just the rectangular coordinate system. Once I get things set up a little bit, then I'll change to polar. Here I'm going to write this as x squared plus y squared plus, now remember, we're doing this as a double integral, so z should not stay z. We're going to write z in terms of x and y using the function given to us by the surface. So here we're not going to leave z squared. We're going to write it as square root of x squared plus y squared, like that. So square root of x squared plus y squared. And again, that one's being squared, which means this one will be squared. All right, now we need to multiply that by the square root of, we're going to have our 1 plus, now we're going to need g sub x and g sub y, right? Okay, so let's go ahead and do that. If we're going to take the derivative of this with respect to x, the derivative of the square root of something is 1 over 2 square root of that something. But then we're going to need to take the derivative of the inner part. We're using the chain rule. We're taking the derivative of the inner part with respect to x. So that's just going to be times 2x. And then over here, we're going to take the derivative with respect to y, and that's going to be exactly the same thing. 1 over 2 root x squared plus y squared. But now, because of the chain rule, we're going to take the derivative of this with respect to y, which is just 2y. Right. That's going to simplify significantly. Here we can write this as the double integral over r of, well, let's see here, that square root and that square cancel out, so I'm going to end up with the square root of x squared plus y squared plus, well, that's another x squared plus y squared. Okay. Over here I'm going to have the square root of, here the 2's cancel out, and I get 1 plus x over the square root of x squared plus y squared. And then over here, the 2's cancel out, which will give me y over the square root of x squared plus y squared. Okay. So note, all I did here was this stays, this gets substituted. Don't forget it's square. Now over here, I have square root of 1 plus, this is going to be g sub x, and this one's going to be g sub y. So 1 plus g sub x plus g sub y underneath the square root. And I'm going to now integrate with respect to a. Here I can simplify this just a bit more. If I give all of these a common denominator, things will be nice. You notice these already have a common denominator, but that one could still use one. Oh, my apologies. I'm forgetting my squares here, aren't I? This should be g sub x squared. And this should be g sub y squared. Pardon me. I forgot my squares here. There we go. So now let's proceed to simplify. Here that's going to be the double integral over r of the square root of. Here I can just double these up. That's going to be double x squared plus y squared. Okay, that one's nice. And now over here that's going to be the square root of 1 plus x squared over x squared plus y squared. That square and that square root go away. Plus y squared over x squared plus y squared, dA. And notice here, these just add up to give me 1. Because that's going to be x squared plus y squared over x squared plus y squared. That's just the number 1. So here that's the double integral over r of the square root of 2x squared plus y squared times the square root of 1 plus this whole thing right here is just the number 1, dA. So here that's going to be the double integral over r. Here I can take the square root of 2. Here that's the square root of x squared plus y squared. And here, that's also the square root of 2, dA. Square root of 2 times square root of 2 is just regular 2, which I can pop out here. So it's going to be double the integral over r of the square root of x squared plus y squared dA. And there's our setup. This is going to be our surface integral. Now, we still need our boundaries. At this point, we may realize, yeah, that doesn't look nice in rectangular coordinates. I have the square root of the sum of squares, and that's not going to be nice. I know that. But given the illustration, I'm thinking cylindrical coordinates are going to be useful, because here I have the stuff over a circle, straight up above. Well, that just looks like a cylinder. So here, we can write this as 2 x squared plus y squared is equal to r squared. So here we're going to write this as square root of r squared. Now remember, whenever you change from rectangular to polar, there's this extra factor of r that follows you around, the Jacobian. So that's going to be the square root of r, and then your dA is going to become r dr d theta. This is that. This one becomes this one. So now all that's left is our boundaries. Right? Here, we can write the boundaries. Notice our object is a circle, but it's not centered at the origin, so we can't just say r is equal to 1. But here, whenever you had a circle that was centered somewhere on the x-axis, the equation to that circle, here, let's go ahead and recall. Whenever you have a circle that looks like this, that's centered somewhere on the x-axis aside from the origin, what you do is you measure the diameter all the way across. Let's call that A. And this is given by r is equal to the is A times the cosine of the angle theta. And where theta goes between negative pi over 2 and positive pi over 2. This is something you see at the end of trigonometry and at the end of Cal 2 as well. So it may not be super fresh in your mind. Also, in case it comes up, if you have this circle, which is centered somewhere on the y-axis aside from the origin, again, you measure the diameter, that's A, and the equation to this, all the stuff inside, is r equals to A times the sine of theta. Okay? And here we're going to take theta, again, between negative pi over 2. Oop, I don't think y'all can see that. We're going to take theta to be, actually this one should be from 0 to pi. There we go. So just keep those in mind. These come up from time to time. And in fact, we see it here. So here our value of r is going to start from the origin and go out to that circle. So here that'll be 0 up to, note that our circle has a radius of 1, which means its diameter is 2. So here this would be 2 cosine of theta. And then our value of theta is bound between negative pi over 2 and positive pi over 2. All right, so here we can write this as, well, the square root of r squared is just r. Right? And then here r times another r is r squared. So this is double the integral from negative pi over 2 to positive pi over 2 of the integral from 0 to 2 cosine of theta of r squared dr d theta. So that's our setup. That's going to be how we evaluate the double integral over S. And now it's just a matter of, okay, we're going to integrate that. You can try that. If you haven't done so already, you can go ahead and pause the video and see if you can integrate that one. This is just a practice on using a double integral. You might give it a try. All right, so let's go through and finish off that integral. Let's see here. That's going to be, let me just rewrite it. That's 2 times the integral of negative pi over 2 to positive pi over 2 of the integral from 0 to the cosine of theta r squared dr d theta. Okay. The integral with respect to r goes first. So that's going to be 2 times the integral from negative pi over 2 to positive pi over 2 of, that's just r to the third over 3, evaluated from 0 up to double the cosine of the angle theta, like that. Obviously, plugging in 0 makes that 0, so we don't care about that one. But plugging in the 2, that's going to give me 8 cosine of theta to the third over 3. So that's 2 times the integral from negative 1/2 to, negative pi halves to positive pi halves. 0 gives me 0. If I cube this, that's going to give me 8 cosine cubed of theta over, that's just a constant 3, d theta, like that. We can take that 8 thirds and just factor that out. So that's going to be 16 thirds. The integral from negative pi over 2 to positive pi over 2 of cosine cubed of theta d theta. We can go ahead and take off a single factor of cosine for this one. So that's going to be 16 over 3 times the integral of negative pi over 2 to positive pi over 2. We can write this as cosine squared of theta times cosine of theta d theta. And now by the Pythagorean identity, we can take cosine squared of theta and write it as 1 minus sine squared of theta. Like that. Okay, well then that just means that that's going to be the derivative. This one's the derivative of a substitution here. All right. So here we can say, okay, let's just use a substitution now. Let's take W to be equal to the sine of theta, which means dW is equal to the cosine of theta d theta. Okay, so that's going to be 16 over 3 of an integral. That's going to be 1 minus W squared. Cosine of theta d theta, that's just your dW. And then don't forget your boundaries have changed as well. If we have theta is equal to positive pi over 2, then that means that W is going to equal to the sine of pi over 2, which is 1. Okay, so that means that my upper bound should be 1 now. And if theta is equal to negative pi over 2, well, then I'm plugging that in right there. And that's going to give me W is equal to the sine of negative pi over 2, which is going to be minus 1. All right, so there we go. So now we have one last integration to pull off. Here that's going to be 16 thirds times. The integral of this will be W minus W to the third over 3, evaluated from minus 1 to 1. All right, and if we go ahead and plug in those numbers, that's going to give us 16 thirds times. That's going to be 1 minus a third minus, and that's going to be negative 1 plus a third. So that's going to be 2 thirds minus a negative 2 thirds. In other words, 2 thirds plus 2 thirds, that's 4 thirds. So it's going to give us 16 thirds times 4 thirds, which is going to give us 64 ninths. And there we go. This is our surface integral of this function over this surface. Yeah. Okay, let's take a look at another example. Go ahead and recall from our previous section that if you have a double integral over surface area, so double integral over S ds, that's going to be equal to, and we see it done in rectangular coordinates, but we also see it done as a parameter. When it's done with a parameterization, that's written as a double integral over a region R of, that would be the magnitude of R sub U cross with R sub V dA. Right? And actually, I believe we call this D for domain. Not that it really matters. So here we had, if you have a parameterization. So here I guess we should say where our surface was given by a vector valued function of, I guess that should be of u and v. Yeah, where S was given as a vector valued function of u and v, where u and v are parameters. Right? This doesn't change anything about what we're about to do. It simply changes how we actually take this to this. So let's consider an example now. We're still doing the same thing. We're still taking a surface integral of a function over a surface. The difference is now we're going to be looking at that surface through a parameterization. So our next example, let's go ahead and evaluate the double integral over S of xy ds. Notice here there is no z to replace, and that's fine. In the last two examples, we've had an x, a y, and then z gets replaced by some function of x and y. Here, z is equal to 1. So, okay, don't worry about it. It just stays as it is. So here that's the double integral over S, the surface integral of xy over the following surface. S is given by a vector valued function of u and v, which is given as 2 times the cosine of u, comma 2 times the sine of u, comma v. All right. So here's our surface. It's given as a parameter. It's given by a parameterization, and here we're trying to evaluate this function over this surface. We're trying to evaluate the surface integral of this function over this surface. All right. So let's give that a try. Recall that whenever we're evaluating a surface integral over a parameterization, we're going to need to take the magnitude of the cross products of the derivatives here. So let's go ahead and find all of those things. First of all, let's find r sub u. Okay, well that just means the derivative of each of these components with respect to u. All right. In fact, let me write them over here. So r sub u is given by, well, let's see, the cosine of this with respect to u would be negative 2 sine of u. The derivative of this with respect to u would be 2 cosine of u. And the derivative of this with respect to u is just 0. All right? That's a constant with respect to u, so the derivative of a constant is 0. And now I need to find r sub v, and here both of these are constants with respect to v, so both of them are going to be 0. But now the derivative of this one with respect to v, well, that's just the number 1. Okay, so now I'm going to take r sub u cross with r sub v, and let's see what happens there. That's going to be, well, let me go ahead and write that out. R sub u is negative 2 sine of u, 2 cosine of u, and 0. And then r sub v is going to be 0, 0, 1, 0, 0, 1. Okay, so that's going to be 2 cosine of u, I. That's going to be 0, j. And that's going to be 0k. Minus, that's going to be 0i. That one's going to be negative 2 sine of u. All right. And then that one's going to be 0, going backwards, yeah, that's going to be 0 as well. So that one will be 0 as well. So 0k. So putting that together, that's going to give us a cross product of 2 cosine of u minus 0. Okay, so my first component is 2 cosine of u. My second component, that's going to be 0 minus a negative. Okay, so 0 plus 2 sine of u, which is 2 sine of u. And then my third component is going to be 0 minus 0, which is just 0. All right, very nice. So I find my r sub u, I find my r sub v, and then their cross product. So now I can write the magnitude of the cross product as the square root of the sum of the squares of these things. So I'm going to take 2 cosine of u quantity squared plus 2 sine of u quantity squared plus 0 quantity squared, which is going to be the square root of 4 cosine squared of u plus 4 sine squared of u. Squaring 0 gives me 0, so that doesn't contribute anything. I'm not going to add that in. Which is just the square root of 4 times the cosine squared of u plus the sine squared of u. Oh, but that's just the number 1. So here that just becomes 4 times 1, which is the square root of 4, which would just give me 2. All right, so there we go. There's our magnitude of our cross product. Maybe slightly anticlimactic, but it's the number 2. So now we can evaluate our integral. Here our double integral over s of x, y, ds. That's going to become, okay, now note, x is equal to this and y is equal to this. So here, even though we don't have a z to substitute, the x and the y also are going to change. So here we can write this as the double integral over a region R of, let's see here, that x is going to be 2 cosine of u, that y is going to be 2 sine of u, and those are getting multiplied together. And now ds is going to be 2 du dv. All right. Here, this is your x, this is your y, right? X times y. And then this part right here is going to be the magnitude of the cross product of the partials with respect to our area, right? Which is the same as saying ds. Right? So that's your x, that's your y, your ds in a parameterized curve given by a vector valued function, or sorry, not a parameterized curve, in a parameterized surface given by a vector valued function, ds is given by the magnitude of the cross products of the partials, dA. So here's the magnitude of the cross product, and here's your dA. Right? Fubini's theorem lets us do that as a double integral. All right, so now, in fact, here, let's actually do that as a double integral. Let's go ahead and give our boundaries. We've been given our boundaries. Have we been given our boundaries? Oh, we were, and I never wrote those down. That's probably a good thing to have, right? The problem says S is equal to R of UV is given by this, and then they actually give us a couple of boundaries. They say where U is bound between 0 and pi over 2, and V is bound between 0 and 1. Oops, V is bound between 0 and 1. So here they actually gave us those. Sometimes they'll give you an illustration, in which case you have to figure it out, as we saw in the last example, and sometimes they just tell you what the boundaries are. Okay. So here we have, those are our boundaries. Our U goes first, so that's going to go from 0 to pi over 2. And our V is the outer bounds, and that's going to go from 0 to 1. Okay, and there we go. There's our setup. We can clean that up a bit. 2 times 2 is 4 times 2 is 8. So we can even write that as 8 integral from 0 to 1 of the integral from 0 to pi over 2 of sine of u cosine of u du dv. Just like that. Here this one's nice because here the derivative of sine is cosine, right? Derivative of sine of u is cosine of u, which means the derivative, the differential of sine of u is cosine of u du. So here this is like w dw. So the antiderivative would just be w squared. Here you could use a substitution. Take sine of u and call it something else. And the derivative of that something else would be cosine of u, which means the differential would be cosine of u sine of u. You can use a u substitution here. So here that's going to be 8 times the integral from 0 to 1 of the antiderivative of this with respect to u is just going to be sine squared of u over 2, evaluated from 0 up to pi over 2. The sine of pi over 2, that's going to be 1. The sine of 0 is 0, so that one won't matter. So here we can write this as 8 times the integral from 0 to 1. Let's see, sine of pi over 2 is 1. Squared is still 1 over 2. And then 0, well, that gives us 0, so we don't worry about that. And now we're going to take the integral from 0 to 1 of 1/2 dv, which is just 1/2 v. So it's going to be 8 times 1/2 v, evaluated from 0 up to 1. Again, 0 makes that 0, so we don't worry about that one. 1 makes it 1/2, so that's going to be 8 times 1/2, which gives us 4. All right. So our double integral of xy over this surface turns out to be 4. All right, so now before we continue, let's give a little intuition as to what the next part of this is going to talk about. So let's bring back one of these things. Here I have a surface. It's a paraboloid, I guess. Why not, right? Here I have a surface, and on this surface I could define a normal vector. The problem is that there's more than one normal vector that I can define. Let's say I want to find the vector that's normal at this point. Well, one way I could do it is I could define this vector that I have here, sticking straight out. But another way I could define that vector is to do it this way, to go through here and come back out the other side. So for this point, there's this normal vector and this normal vector. So which one do I want? You say, well, you want the one that's toward the front, or you want the one that's toward the top or toward the outside. How do I define that? Right? You say, well, it's pretty clear right here. This is the top. Okay, what if I do this to it? Is that still the top, or is this the top now? All right. What if I turn it sideways? That's not the top or the bottom. That's the side. So how do I designate the side? So how do I tell which direction I want? That's called an orientation. Whenever we have a surface, we can orient the surface to give ourselves a concept of direction. Now, it's not quite as simple as to say inside or outside, but it's, well, almost as simple. So consider a surface that would look something like this. All right, and let's give that surface with an equation. Here, let's say z is a function of x and y. Now, incidentally, in this chapter, we're doing everything z as a function of x and y. There's no restriction to that. You could say, oh, I want x to always be a function of y and z, or I want y to be a function of x and z. Here we're doing z as a function of x and y. There's no reason why it has to be that way. That's just what we choose and what we stick to. But now here's a surface given by that equation. Okay, so now let's say I pick a point on that surface. Let's say I pick this point here, and I want to make a line that is normal to this point. Well, there's two ways to do that. There's this line here, and then there's a line that comes in and comes out the other side. So both of these are normal vectors. Here we're going to call this one n, and this one we call it minus n. All right? Now you say, well, now how do I even know which one I want? How do I know which one I have? Well, that's up to you to define. Whenever you first start, you pick one direction and call that the positive direction. Some people might call that up. Some people might call that out. Some people might call that forward, or whatever. The language is imprecise, but the symbols are always the same. Here, this is going to be up to us, how we define it. All right? So once you have one vector, that's going to be your normal vector. We're going to use that as an orienting vector. Even though, again, it can be in any direction in terms of any variable, here, because we generally want to define our function as g of xy gives you z, here we generally consider z as being up and down. So here, even though this isn't always the way it has to be, for us, we're going to call this the upward oriented normal vector. Okay. It doesn't have to be up. It can be right. It can be down. It can be anything. But for the purposes of our notation, And to be consistent, we're going to stick to this one is going to be the upward oriented normal vector, and this one is going to be the downward oriented normal vector. Unless there's a reason why we really have to, we're generally going to stick with this one. Orienting vectors should not be taken for granted in general. However, in this class, they can be. Not every surface is orientable. It sounds strange, but there are some surfaces that don't have a clear sense of, oh, this way is up and this way is down. The most famous of those you can actually buy these. Someone actually found a way to make them out of glass. They're the strangest things. They're called Klein bottles. You can look that up. Oop, I don't know how to spell. Klein bottle. And it is what's called a non-orientable surface, where technically there is no. It is kind of shaped like a bottle, but there is no clear inside or outside. In other words, if I were to take my my bottle and I were to put a little drop of water on it, I could then rotate that bottle, and eventually the drop would be, quote unquote, inside the bottle. And I say quote unquote because really there is no inside. And if I continue to rotate the bottle, eventually it'll come back to the outside. It's the strangest thing. There's another version of a Klein bottle. This is a more elaborate version. The more simple version, which in fact is something that you can make at home with paper, is called a Mobius strip. Anyone interested in strange geometries, look these up. You can make one of these out of a strip of paper. These are harder to make, but you can buy one on the internet. And there are actual Klein bottles you can buy. Anyway, there are surfaces that are non-orientable. These are examples of non-orientable surfaces. However, in this class, you can take for granted that every surface that we have will be orientable. For the most part, any surface that you've seen in this class, whether it be a cylinder, a hyperboloid, an ellipsoid, a plane, a curve, a line, all of those things. Every surface that you've seen is orientable, and we won't have any that aren't. But here, it would be an incomplete description of this stuff if I didn't mention that at least these exist. Okay. Now, how do you find this normal vector? Well, it's the same normal vector that we saw in a previous section. Namely, it comes from the gradient. So here, if we say z is equal to g of x comma y, we can write this as follows. Z is equal to g of x comma y. Okay, let's go ahead and write this as a single equation equal to a constant. So here I'm just going to subtract g to the other side. So I'm going to write this as z minus g of x comma y is equal to 0. So now what we're doing is, instead of thinking of this as a three-dimensional surface, I'm thinking of this as a three-dimensional level curve of something that's in 4 dimensions. We saw this back in chapter 13. Now that these 3 dimensions are thought of as the level curve of a 4th dimensional object, to find the vector that's normal to that level curve, we're going to use the gradient. So here we're going to take this function here, z minus g of x comma y. This is going to be called g of x comma y comma z. It is a function of 3 variables, technically, right? X and y and technically z. So the normal vector is going to be given by the gradient of this vector g of x comma y comma z. For the purposes of orientation, we don't generally want a vector that is very long. We want a unit vector because we don't want it to affect any of our computations because it has a different magnitude. We only want to consider the orientation. So here we generally consider the normal vector as a normal unit vector. So here we're going to go ahead and say, okay, well, whatever this is, we're going to go ahead and normalize it. We're going to divide by the magnitude. All right? So this is what we mean. When we say n, we mean take your surface, think of it as the level curve of a 4th dimensional object, and then take the gradient that's been normalized to give you the unit normal vector. If you want the normal vector in the opposite direction, then that's literally just the negative of that one. So negative of this is going to be negative the gradient of g of x comma y comma z over the magnitude of g of x comma y comma z. Because you'll remember from trigonometry or pre-cal, wherever you first learned about vectors. If two vectors have the same description but with an opposite sign, they're traveling in the same direction, or rather, they're traveling along the same line but in opposite directions. So here, these are opposites of each other. This one's upward, and this one's downward. And unless there's a very good reason why we want to use the downward one, the upward one is the one we generally stick to. Generally stick to this one. Okay, so now that we have a concept of orientation, the last thing we're going to look at in this section is the concept of a flux integral. What a flux integral is, it has to do with flow rates. So here I have a filter. I use this to make my morning tea. Now, if I have this filter, I can pour a stream of water or tea here, and the tea leaves will get trapped here. Okay, fine. Ignore the tea leaves for a second. If I'm dropping water through here, it's going to flow through at a particular rate. Now, if I happen to drop water through here very, very quickly, a lot quicker than I usually would from a small pour of a teapot, here, some of the water would get caught up just a little bit. All right? Here, this is not solid. It's a mesh, but still, water has tension and it would get caught up. If I poured water here quickly enough, it would not come out the other side quite as quickly as I poured it in. So there is a rate at which the liquid will flow through here. Well, how do I compute that? Well, we're in calculus. We're going to compute it by approximating little tiny bits. So imagine you have this solid, you have this surface, and again, it's made up of a mesh. Here I'm just drawing a cartoon version of my sieve here, and I'm going to let something pass through it. I'm going to have a liquid flowing through. That's a vector field. Consider that I have a vector field. Now, of course, in my example, the vector field is just the drops of water that are flowing from my teapot. But here, this could be wind. This could be any fluid. Here we have a vector field, and that's F. Now, this vector field is flowing through here. Okay, well, one thing about flow rate is that we can have it going forward or backwards. There's a difference between a certain amount of liquid flowing this way versus this way. So when I have my flow rate, I need to make sure that there's a sense of orientation. I need to make sure I know which way I'm talking about. Is my liquid flowing that way or this way? Right? For this example, it seems pretty obvious, but what happens if I had a vector field where things were rotating? What happened if I had a vector field where things were going in every direction? Well, I want to know, okay, what's my net effect? Maybe sometimes things are flowing out, sometimes things are flowing back in, up or down, and what I want to figure out is my net effect. Okay, maybe right here things are flowing this way, but maybe over here things are flowing this way. What happens overall? So we're going to need a concept of up and down or a concept of in and out or something like that. So we're going to have a orienting vector, and again, for our purposes, we're going to use the upward facing orienting vector. Okay, now I want to figure out how much of this flow is going in that direction. Okay, well, that's simple enough. What I want to do is I want to take the amount of liquid that's coming through. Okay, well, how do I do that? Well, take a little tiny patch of your surface area. Little tiny patch of surface area. Okay, well, from that little tiny patch, you can imagine that the amount of fluid that's coming through is a little column. What I want to know is how big is this column? If this is a little tiny amount of liquid, of fluid, well, then it's not flowing through very quickly. If it's a very big column, well, then it's flowing through very, very quickly. Well, yeah, but you got to be careful here. No one ever said that your column had to be perfectly parallel to your normal vector. Given my illustration here, it's clearly not, because after all, if that's my normal vector, the vectors of my vector field are going this way. Okay, so if the vectors of my vector field are going this way, and in this simplified example, then I don't have all of that flow going in the direction that I consider the direction I'm looking at. I don't have all of it flowing out, so to speak. Okay, so I don't really want all of the vector f. I just want how much of that vector f is in the direction of n. Oh, well, that's just a dot product, isn't it? So here, the column here has a volume. This column is a column of liquid. I basically said, okay, let 1 second of time flow. Okay, how much liquid flowed through this little patch in that 1 second? Oh, that liquid fills up this amount of volume. Okay, well, that volume is given by a base times a height. Okay, just like that. Now this base is just that little tiny patch of surface area. So here this base is going to be a delta S. Now, of course, I have a bunch of them, so I could say delta S sub I. And here the height is just how much of this vector is in this direction. Well, that's a dot product. If I give you two vectors and I want to know how much of this vector is in that direction, that's just given by a cross product. A dot product. F dot n. Actually, it should be F dot n over the magnitude of n. But again, the magnitude of n is going to be 1. All right, so here, let me actually write that. Thinking back to trigonometry, when you project a vector onto another vector, it's going to be the magnitude of that projection is F dot n over the magnitude of n. All right, if I'm projecting F onto n. But since this has a magnitude of 1, right, over here, that's a unit vector. Has a magnitude of 1, then that's going to give me that the volume is equal to F dot n delta S sub I. Right? Or I guess I should say it's approximately equal to that. So from this, we get the volume of this, which means if I want to find out how much volume is going in that direction overall, if I want to say, okay, here's my object, I'm going to have stuff flow through here, and maybe some stuff will deflect outwards, maybe some stuff will strain in different directions. But what I want to know is how much of it is going to go right this direction, how much of it is going to go straight down, or straight up, or straight left, or straight right. Then, given that direction, this is the amount of fluid that is flowing in exactly that direction. So if I want to find the total volume, again, that's going to be approximately the sum of all of those. The sum as I goes from 1 to n of F dot n delta S sub I. Okay? Oh, okay, so that brings us to our definition. Definition, let f of x comma y comma z be a vector field. All right, that's our vector field, like my flowing T or whatever. That's my vector field. Here we're going to have that vector field represented by a 3-component vector-valued function, m, n, and p. Now, because of the way that we're going to evaluate these, we need m, n, and p to have first partial derivatives. We need those to be continuous on the surface. The surface S. Okay, that surface S is, again, just like my strainer, just this object here. This is my surface S. Okay? Now, that surface S is oriented by a unit normal vector. There's a unit vector that is normal to the plane, the tangent plane of our surface at every point, and we're going to be using that unit normal vector as a sense of orientation. In other words, that vector, that one vector there, is considered to be out or up or whatever orientation, whatever direction we wish to define that as. Then the double integral over the surface area of f dot n is called the flux integral of f across S. The visual for that is how much flow is going in this direction through this object. Right? Here's your vector field. Here's a fluid. How much of that fluid is going in that direction through that surface, through that sieve, through that strainer? How we do that brings us to a theorem. We're going to begin with a surface that's oriented. Let S be a surface oriented by a unit normal vector n. Given by where S is given by Z is equal to G of X comma Y. like that. And let R be its projection onto the xy plane. Let R be the projection of S onto the xy plane. Then the flux integral of F in the direction of n across S is given by the double integral over R of F dot, here let me write this as negative G sub X, comma, negative G sub Y, comma, 1 dA, or it's equal to the double integral over R of F dot G sub X, comma, G sub Y, comma, negative 1 dA. The difference between these, here, the third component is positive, so this is the typical unit normal vector facing quote-unquote upwards. Here, this one's negative, so this is generally what we define as the unit normal vector being downwards. So here we have oriented upwards, and here you would have oriented downwards. Basically, here you're using just regular n, and here you're using the negative n. All right? The proof of this is, I'm not even going to give the full proof, just a quick little sketch of this. After all, most of this remains the same. We know that we know that surface integrals can be evaluated as double integrals. Here, the vector field remains the same. Nothing about it has changed. Here, the only part we really need to concern ourselves with is how did this become that? All right, well, I have a unit normal vector, ds. All right, so here f is staying f. Here we're going to see how this changes into this. All right, so here I'm going to be focusing on the upward orientation. Assume oriented upwards. Then you have that n is given by the gradient of g of x comma y comma z over the magnitude of the gradient of g of x comma y comma z ds. Okay, and after all, this is just the definition of our normal gradient of our normal vector, as we saw just a moment ago. N is given by the upward oriented n is given by the gradient of capital G over the magnitude. But remember, the gradient of capital G is the gradient of this thing, z minus g. So here we can write this as the gradient of z minus g of x comma y over the magnitude of the gradient of z of g of xy ds. Okay. Well, now the gradient of this, well, remember, the gradient is just the derivative with respect to x and y and z respectively. So here, the derivative with respect to x, well, that goes away, and I'm just left with negative g sub x. Because right here, this doesn't involve x, only this one does. So the derivative of negative g of x is negative g sub x. Okay. Over here, I'm going to say the derivative with respect to y now, and again, same thing, that goes to 0, and this becomes negative g sub y, and the derivative with respect to z is just 1. That doesn't involve z. Divided by, now the magnitude of this vector is given by the square root of the sum of the squares of these things. Of these things. So this is going to be negative g sub x squared plus negative g sub y squared plus 1 squared, like that. But now ds, as we saw in a previous section, and as we see here at the very beginning of in our first theorem, ds is simply given by the square root of 1 plus g sub x squared plus g sub y squared. So here that ds, is given by that dA, right? ds is given by that square root dA. So that's going to be given by the square root of 1 plus g sub x squared plus g sub y squared dA, which is equal to, notice these are exactly the same. All right, negative g sub x squared is the same as positive g sub x squared. So here, these are the same, these are the same, and these are the same. So here, these divide out perfectly to give me just the number 1. And now I'm just left with a vector negative g sub x, comma, negative g sub y, comma, 1, dA. So coming back up over here, f stays the same, and nds can be replaced with the vector negative g sub x, comma, negative g sub y, comma, 1, dA. And now it's a double integral over a region R. Well, if we're taking a double integral over a region R, that region R must be the projection of S onto a plane. And since we're dealing with the variables x and y, well, then it must be a projection onto the xy plane, which gives us our theorem. Notice here I did gloss over a few things. This gives you the main part of the proof, but I did gloss over a few things like, for example, wait, how did you know that's a projection? Things like that. So here, this is the main part of the proof. The rest of it is just these little minor details, which frankly can just be done with a sketch. All right, here's a surface. It's in 3 dimensions. I need it to be in 2 dimensions, so I can do that by a projection. 3 dimensions can project down into any one plane, as we've seen in previous sections. And since I'm dealing with only x and y here, well, then naturally I think I'd want to project down onto the xy plane. Things like that. So here, this is, I'm not going to write QED here because that technically isn't really the full proof, but it's good enough for our purposes. So let's go ahead and compute a flux integral to finish off this section. All right. So let's see here. Our last example is going to be, oh, that's the wrong pen. We're going to evaluate the flux integral. Anytime you see f dot n ds, that's a flux integral. We're going to evaluate the flux integral given that f of x comma y comma z, given a vector field, is given by x, y, z, and that the surface S is given by x squared plus y squared plus z squared is equal to 36 in octant number 1. Here we have a sphere of radius 6, but notice we don't want the full sphere. We only want the part in octant number 1, so we only want the part of the sphere where everything is positive. So here, 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 and this way, right? We only want the part of the sphere where everything's positive. All right, so that, what, 1/8 of a sphere. Notice here that this sphere, if you were to squash it down onto the xy plane, that gives you this quarter circle in the xy plane. Or in other words, this 1/8 of a sphere rests entirely on top of this quarter circle, and that quarter circle is just the quarter circle of radius 4, right? Of radius 6, because after all, here every trace is a circle of radius 6, and that includes the one on the xy plane. Okay, so this is going to be our region R. Okay, so let's go ahead and do that. This is going to be a double integral over the region R, which we describe here, of f dot, and now n ds can be written as negative g sub x, comma, negative g sub y, comma, 1 dA. All right. Note this is in 2 dimensions, so here our boundaries are going to be with respect to x and y only. You might try that now. You have everything you need. Here you have a function which defines your surface. You can use this as your g. Now remember, g should be a function of x and y only, so make sure you modify that accordingly. F is given. This can be used to give you g, which you can use to find this vector. And once you take the dot product, you'll integrate over this region. Go ahead and pause the video and give it a try. See if you can evaluate the flux integral. And once you have an answer, go ahead and unpause, and we'll finish this off together. All right, so here we're going to take the double integral of, well, f is given to us, right? It's x, y, and z. Well, no, you can't use that. Because remember, this is going to be a double integral. You can't use three variables. So here, we're going to have to use this to tell us what z is equal to. Okay, well, that's not so bad. Let's just solve for z. Here, we could take z squared is equal to 36 minus x squared minus y squared. And I want just z, so let me take the square root of both sides, and I get z is equal to the square root of 36 minus x squared minus y squared. I don't have to worry about plus or minus because here I want z to be strictly positive because it's in the first octant. So here I'm going to write f, but I don't write it as x comma y comma z. I write it as x comma y comma that thing right there. This will be the single biggest mistake that people make in this section, and that's when they transform a surface integral, whether it be a flux integral or otherwise. When they transform a surface integral into a double integral, they will neglect to replace one of their variables. Remember, this is a double integral. You can't integrate three variables. So we have x comma y comma square root of 36 minus x squared minus y squared. Dot with, here we're going to take negative g sub x. Okay, well this is g right here. This is your g of x comma y. So g sub x is going to be the derivative of this with respect to x. Okay, well the derivative of a square root is 1 over 2 times that square root. But then the chain rule says take the derivative of the inside, which is going to be a negative 2x. 2's cancel out, and I get negative x over the square root of 36 minus x squared minus y squared. G sub y is going to give me almost exactly the same thing, except the y here instead of an x. You can go through g sub y, and that'll give you negative y over the square root of 36 minus x squared minus y squared. Okay, so here, if I take the opposite of this, that's going to give me my my negative g sub x. Okay, so that's the positive one, but I want the negative one, so I'll just change the sign. So that's going to be x over square root of 36 minus x squared minus y squared, comma, same thing here, that's the positive one, but I want the negative of that, so negative of a negative makes that a positive. Y over square root of 36 minus x squared minus y squared, comma, and that last one's always the number 1. Okay, just like that. And then dA. So that's going to be the double integral over R of, remember how a dot product works? It's this times this. So that's x times x will give me x squared over square root of 36 minus x squared minus y squared. Plus, here that's y times y, which will give me y squared over square root of 36 minus x squared minus y squared. Plus, 1 times that is just that. dA. Here, if I give all of these a common denominator, I can write this as the double integral over R of x squared plus y squared plus 36 minus x squared minus y squared all over the square root of 36 minus x squared minus y squared. Okay. Here, I just left these the way they were with the same denominator, put them together. Here, I multiply top and bottom by this denominator, which makes this square root go away. Okay. So that stays there, that stays there. This gets rid of its square root when I give these a common denominator. And now, a lot of terms disappear on me. That's a constant, so I can go ahead and factor that out. So that's going to be 36 times the integral, the double integral, over the region R of 1 over 36 minus x squared minus y squared under a square root, dA. Just like that. So now, I look at this, and I look at this, and I think, yeah, definitely polar coordinates. Polar coordinates here, absolutely. I have the sum of squares in here, right? That's minus x squared plus y squared. And over here, I have a quarter circle. there's no question. That's got to be polar coordinates. So here we're going to say 36. We're going to take a double integral of 1 over the square root of 36 minus x squared plus y squared is r squared. So negative x squared minus y squared is minus r squared. dA, when changing into polar, is going to be r dr d theta. And here, the value of r and the value of theta, I can look up here. And I note that r starts at 0 and goes out to a maximum value of 6. I start from my pole and go to 6. And then over here, my value of theta, well, that's going to be theta is equal to 0 up to theta is equal to pi over 2, right? A quarter circle from 0 to pi over 2. And there we go. So there's our setup. This is double integral is equivalent to our flux integral. So now we'll be able to integrate this and get our result. All right. Here, let me go ahead and use a u substitution. Let me not, yeah, that should be fine. So let's go ahead and use a u substitution. U is equal to 36 minus r squared, which means du is minus 2r dr, which is almost exactly what I have. I have minus 1/2 du is equal to r dr. So here that's going to be 36 times a double integral of 1 over, I'm taking this whole thing and calling it u. This r dr is going to be negative 1/2 du. This. Here, that doesn't affect the outer bounds, right? This only affects the this one in here. So I'm still integrating from 0 to pi over 2 for theta, but what I've done is I've changed this integral using a u substitution. Well, if I've changed the integral, I should also change its bounds, right? Here, u is equal to 36 minus r squared. That means if r is equal to 0, that means u is equal to 36 minus 0 squared, which is 36. So that lower bound should be 36. The upper bound, if r is equal to 6, that means u is equal to 36 minus 6 squared, which is 0. So I've changed my boundaries. All right. 1 over square root of u, that's negative 1/2 du, and that has these boundaries changed to u instead of r. Let's see here. Let me take that... I can take the 1/2, pull it out, so that'll give me 18. Here, I can get rid of this negative by flipping these bounds. So that's going to be from 0 to 36. Right? The 1/2 came outside, the negative flipped those boundaries, and now I just am left with this integral here. And now things look reasonably nice. The integral with respect to u, I forgot my d theta here, didn't I? There we go. The integral with respect to u of 1 over root 2, or in other words, the integral of u to the minus 1/2 is going to be, what would that be? 2 square root of u. And that's evaluated from 0 up to 36 d theta. Here, if I plug in 0, the square root of 0 is 0, so I don't care about that. But 36, square root is 6, times 2 is 12. So this will give me 18, the integral from 0 to pi over 2 of 12 d theta. I can factor out that 12, and that'll give me 12 times 18. That's going to give me 216, times the integral from 0 to pi over 2 d theta, which is just going to be 216 theta evaluated from 0 up to pi over 2. Obviously, 0 keeps that 0, so the only thing that I worry about is pi over 2. So this will give me 216 times pi over 2, which will give me 108 pi. 108 pi. That's my flux integral. Physically, what that means is if I had this surface and I had a unit normal vector facing upwards. Here, unless we have a reason why we want to use a different unit normal vector, we typically consider straight up to be our unit normal vector. Okay, so what this is saying is, okay, here's your vector field. You have vectors flying in there in these directions, And as those vectors pass through here, how much of those vectors, how much of that fluid is going in that direction? Right? It's a flow rate, so this would be, per unit of time, per second or whatever the unit of time is. So these vectors are flowing through this surface. How much of that flow is in that direction? Oh, there you go. That's how much it is per unit of time. All right. You might say, well, okay, we're always going to use that normal vector straight up. Then why did you even define the other vector? There's going to be one case where you may wish to consider both vectors. In fact, you're going to have to. And that's sometimes you're going to have a closed surface. Here, I'm not going to go through a full example. I'm just going to sketch the illustration here. Let's say this is our surface, S. Okay, then what I want to figure out is the flow rate through this surface. Well, see, here's the thing. That may be, in fact, there's a good chance it's going to be 0. Because if your flow rate is given by a vector field where everything is uniform going this way, you may end up with, well, just as much flows this way as it does this way. All right? So how do we quantify that? How do we even say which direction we're going to favor? What I mean by that is, why should we have the upward normal vector here? Couldn't we just as easily have the downward facing one or the one facing this way or this way? Whenever you have a closed surface, it's hard to tell which direction is a reasonable direction. That's why when you have a closed surface, we generally don't worry about up or down in the traditional sense. For a closed surface, we care about the outward facing normal vector. So for a closed surface, look at the outward facing normal vector. What we mean by that is look at not how much stuff is going up or down or left or right, but rather how much stuff is coming out from here. Right? How much of your flow is coming out versus how much is going in. In later sections, we'll talk more about the language of this. But if you have more stuff coming in than you have coming out, that's called a sink. All right? More stuff is going toward there. It's draining through here. There's something in here that's absorbing everything. If, on the other hand, you have more stuff coming out than coming in, then stuff seems to be coming from in here. It's where it's originating. This is called a source. So we'll talk more about the language in later sections, but that's the difference between a source and a sink. Now, of course, you may notice that if you want to look at a vector that's facing outwards, this one is no longer necessarily going to be useful to you. And you say, well, that is facing outwards. Yeah, for this part. But if you have that same unit vector over here, well, then that's going to be going inwards. So here, the one that's facing outwards would be going in this direction. So here, this would be your unit normal vector, the one facing upwards. But here, this would be the negative unit normal vector, the one that would face downwards. So this is going to be a reason why you might want to use, why you might want to define both unit normal vectors, because in a later section, we're going to be talking about closed surfaces. And when you're talking about closed surfaces, it's not really as useful to talk about up versus down. You'd rather talk about in versus out. This encapsulates some volume. I want to know how much of that vector field is coming out of that volume versus how much is going in, whether it's a sink or a source. And as such, I don't really care so much about up all the time or even down all the time, but outwards. So what will generally be done is you're going to split this into two regions, the upper part and the lower part. The upper part will be oriented upwards because that's which way out is. And the lower part will be oriented downwards because, again, that's where the outward part is. But we'll see that in later sections. Right? And that is it for the section here. For an assignment, go ahead and try problems 13 through 27 odd. And that should suffice. Okay. If anybody has any questions, comments, problems, please make a note of those and reach out to me, and I will get back to you in due order. Yeah? And I hope everyone has a nice day.